Okay, yeah, so let's get started. Welcome everyone to this webinar with my name is Jesper Molin from Sectra, and I'm head of task 4.5, and so part of Word Package 4 mainly in Bigpicture, where we develop a lot of tools and software that's going to be used by the infrastructure. And today I have the honor to present my dear colleague Eric, who is sort of, I don't know exactly but he's the DICOM geek of the project, and he has been working on developing a lot of great research tools that he's gonna show and explain the thinking about today. So I'll before leading over to Eric, we will do like this. So if you have any questions during the talk, just write the questions in the chat. I have a copy of Eric's presentation, so I will see if it's a question that he will cover anyway. Then I will not take it up. But if there is something which fits really into the presentation, I will bring it up directly. Otherwise, the remaining question, we will do a Q&A in the end. And then in the Q&A, you might also, if you want to, you can just turn on your video if you haven't done so, and just ask the question right away. And we will have some interactivity in the end. And with that, I leave it over to Eric.
Okay, thank you, Jesper.
Maybe one additional comment. I think most people are aware, but this meeting is being recorded also so that it can be seen by other people. And then go ahead, Eric.
Okay. Is the screen sharing working?
Yes, I think so.
Yeah.
I see it.
You see me too, or?
Yeah, I see you too.
So we already gone through this. A little bit more about me. I have a background in engineering biology and a PhD in organic bioelectronics from Linköping University. That's not so much relevant to what I do right now. So I've been research engineer here at Sectra since March this year. And when I'm not working or spending with my time with kids or family, I like to ride bicycles fast. A bit about this presentation. So it will be an overview into what DICOM BSI format is. We also talk a lot about the tools that we have developed in this task 4.5 to work with DICOM. And the aim is that this will be useful or informative for those that will work with DICOM in the Bigpicture project. We're thinking of those who are doing VC viewers or AR researchers, or maybe those, or hopefully for those also who are going to upload slides, because the slides are going to be in DICOM format. But we also hope that it will be interesting and fun to listen to for others as well. And a little bit context. What is task 4.5 and how does it relate in Bigpicture? So the title of task 4.5 is to develop a technical implementation of the open digital slide annotation and metadata formats. What we do in task 4.5 is that we define the DICOM format that we're going to use in the repository. We're also making conversions tools to convert from other VC file formats to DICOM. And what's coming up is also tools for anonymization and tools for uploading these slides to and related metadata to the repository. Related deliverables for this is one that we are working on quite heavily right now, is the report on unified open digital slide and annotation format specification that should be done within a month. And also the delivery 3.3, which is the report on defined and first collected dataset that is going to be done in month 18. So the outline for the rest of the presentation is that I will go to what the VSI are from a technical perspective and some of the formats that VC can have. And then we'll go into more a demo mode with how you can read the VSIs using VC DICOM, or you can convert them using the DICOMizer, and also show how right now it's possible to process data sets, at least small data sets, and we'll end with the conclusion and discussions and so on. So VSIs, of course, they are images of slides that have been taken with the scanner. One thing that is very important to know is that they are, as images, they are very large. So if you scan a 30 by 20 millimeters slide or piece of a slide at 40x, which is typically the highest resolution, meaning 0.25 microns per pixel, you will get an image that is around 10 gigapixels compared to what you get from your mobile phone might be, I know, 10 megapixel. So it's 1,000 times larger. And uncompressed, this will take up 30 gigabytes of memory. So one way to handle these, to store them, is to, of course, compress them. And one popular compression method is JPEG, giving you maybe a compression ratio of 20 to 20x with still okay quality. And when you compress with JPEG, pixels will be grouped into these minimal coding units. They are typically 8 by 8 pixels that you group them together. And these are then stored in the file from left to right and top to bottom in like this order, going on like this. Along with this is that if we want to look as part of this very large 10 gigapixel image, if it's uncompressed, we know how big or how big size each pixel takes. If it's a RGB image, meaning red, green, and blue, and each channel is 8 bits, we can calculate, okay, we want to read from pixel number 1000 or something. We can calculate how far into the file do we have to go before we come to this region of interest, and how far should we read before we get to the next part of the region of interest. But as we have compressed these MCUs, we don't know how long they are in the file without decompressing them. That means that if we want to read this region of interest from this 10 gigapixel file, we have to start by reading all the MCUs starting from the top row, going in here, calculating how many pixels have we read, and going in the next row, we're still not on the region of interest. Now we found the starting point of the region of interest, read parts of the region of interest, and then we come to the end here, and we have to continue reading things that we don't want to read until we come back here, and we have to do that until we found the complete region of interest. And as the image is big, we have to read a lot of data that we don't want to read. Means that random access to parts of this image is very difficult. A way to fix this is by tiling the image. And when we tile the image, we typically do that by doing a grid of rectangular tiles that are, for example, 512 by 512 pixels wide. It would look like something like this. And another thing that we do is that we make an index of where these tiles are in the file. So if I want to read this tile, I go to the index, looking up where is the tile that is positioned at position X and Y, and I get the exact file offset, so I can jump to this offset in the file and I can read just this tile. Meaning that if I want to read this region of interest, I jump to this tile, I read this tile, I read this tile, this tile, this tile, this tile, and so on. And I can merge these tiles together and then crop out the region of interest. Oh yeah. This means that I get fast random access reading, and it's the same procedure wherever in the file I am. I just have to jump to the relevant tiles, and also I can move around in the image quite fast, so fast panning. The similar technique is used, for example, for mapping services here, like for example, with Google Maps showing the sector office. And I will use this to illustrate another problem, which is also both for mapping and for VSIs. So say I'm at sector office and I want to go to Linköping Central Station. This is about 6 kilometers, meaning that with the view that I have here, it's about 50 meters I can see. I have to then change view about 100 frames before I can get to Linköping Central Station. And this is of course annoying. A way to make it much easier is if I can zoom out and get the complete picture. Now I can quickly see that sector is here, and central station is here, so I can figure out the best way. But when I zoom out, I have around, for this image now, 2,500 more information in the image, meaning that if I would take this image from all these small zoomed in parts, it will take 2,500 longer to generate this image. And I would also have a much larger image in my memory that I would have to downsize to get to a reasonable viewable image. So you have the same problem for vsize. When you want to zoom in and out, you have a larger region of interest, meaning more tiles and more pixels to read, and it is slow. And the solution for this is something called pyramid levels. And in pyramid levels, we have our base image in a bottle, which has very high resolution and is tiled. And from this base image, we take, for example, a group of 2 by 2 tiles. And from this tile, we downsample that to one tile and in a level above this. So we create a new image, which is then a downsample of the original image. And from this image, we create another downsample version, and so on until we have this pyramid where the topmost levels are maybe 1 megapixel in size. And when we want to zoom, we can just determine which of these pyramid levels is best suitable to show a picture with this region of interest that you have and what the level of detail that you want. And of course, making these additional images takes the space, and roughly you will have about 30% larger file when you make these pyramid levels. But the advantage of how fast you can zoom in and out, it's well worth it. And one way to see this also is that if, for example, you have scanned your baseline bottom level in 40x, you would have a 20x, something that is almost like 20x in the above level. And then, of course, it's in pixel size. You still have the 40 times objective depth of focus in this image. And then you go to 10 times magnification and 5 times magnification. So different way that the vsize can look like in terms of tile arrangement. The most straightforward way is that you have these rectangular tiles and they are very nicely and uniformly arranged. Another way is that you, instead of having rectangular tiles, you have these thin stripes. Another thing that is quite common is that these tiles are overlapping. And something that also is quite common is that some tiles that are not showing anything that's interesting, those are lacking in a file, so it's a sparse tile. In DICOM, you can have all of this except for overlapping tiles. And in general, for performance reason, it is preferred to have non-overlapping tiles because that means that you don't have to cut out parts that you're not interested in. You want to have rectangular tiles because it's more efficient to read. And you want to have a fully tiled arrangement because that's also faster. So this fully tiled tile organization is the best. Going into how DICOM files looks like, this is a dump from a DICOM file. So DICOM files are in binary. So this is a tool that reads the binary file and prints it nicely in text. And what you see first here is all the tags. So every element starts with a tag saying that identifying what kind of information you have. And the tags have two parts. It's a group tag and an element tag. After the tag, we often have this value representation saying what is the value type of value you have. So it can be integer or short string or other things like date and what else do we have here? Binary data. Then you have the value. Here they are decoded. And also this tool gives us the tag name for a corresponding tag, so it looks that up for us. Interesting things we can see here in this dump is, for example, the transfer syntax up here. We see that this file has a transfer syntax of JPEG, meaning that the image data that we will find is in this file, it will be JPEG. Next, we see here in the SOP class UID, it is a BL Vols slide microscope image, saying that this is a VSI image. Up here in the image type, we see that the image size is volume and resampled. Meaning the volume means that this file is part of the pyramid, and resample means that it's not the base layer, it's one of the downsample layers. And the SOP instance UID is just a unique identifier for every DICOM file, so every DICOM file should have a unique identifier. And then, of course, we have other things here, for example, the manufacturer and so on. So the DICOM file has a lot of tags. So how do we know what tags are needed and what do they mean? One thing you can do is that you go to this very nice DICOM browser by Analytics, and you can, for example, look up what is needed for a old slide microscope image. If you go in here, we see a lot of so-called modules. So each of these things are modules. We have a patient module, we have an image pixel module, we have an optical path module. And we can see here, it's either M stands up for that this module is mandatory to have in this for a VCI image, or it can be user optional to have this. If we open one of these modules, we see the tags that are defined in the module. So we have, for example, the study date tag. And if we click on this, we will open up another window showing the tag numbers and more information about it, but I'm not going to show that. And we also have these numbers here. So 1 means that this tag is required. For example, each file needs to have a study instance UID. If it's a 2, it means that the tag is required to be present, but it can be empty. And if it's 3, then it's completely optional to have it in. And the way DICOM organizes the data or objects is described in this figure, where we start with having a patient up here. So the patient can be part of one or more studies, and the study will contain one or more series. And the series is where we store files. And it can be different types of files in a series. So you can have image files, you can have structured report or measurements or annotations and other things. When it comes to VSI, VSI from the same study or case on a patient, they would be grouped together in a study. And each VSI is then its own series. And this series will then contain image files where each image file will represent one pyramid level. So for each pyramid level we make one image file that goes into this series. If we have label or overview images, they also go into this series. And we also have each series will have an equipment that generated it. So for example, a scanner. And you can also specify, or you should specify, a frame of reference for a series, saying that all the measurements are in reference to a certain position in the slide. And this is how a typical set of files for a DICOM VSI can look like. We have the base level, this biggest level, it's this 400 megabyte image or DICOM file. And then we have the downsampled files listed next under it. And each file here is then 4 times smaller, indicating that this is downsampled by half. And in the end, we also have a label image here. And the relation between files is that each file will have a series UID, so we can group VSI together into a series. That is, all these files will have the same series UID, saying that they are from the same scanned slide, or from the same instance of scanned slide. And we can also group these slides together by the study UID, and we can group them together to a patient by the patient ID. And file names or how we organize the folders, etc., it's not important. It is this identifiers that makes it possible for us to say that this file belongs to this image. So in Taskforce 4.5, we have developed 3 tools for dealing with DICOM VSI. The first one is VC DICOM, which is used for reading and writing. OpenTile is a tool for like getTile for TIFF VSIs, and VC DICOMizer is a conversion tool for other VSI formats of DICOM. And you can find all these tools on the EMI Bigpicture GitHub page. Going on to VC DICOM, this is a package for reading and writing DICOM, and you can, since like 2 weeks ago, you can do pip install VC DICOM if you want to use it. I will go on to show how it can be used. Is this view okay, or should I use full screen here? Or should it be smaller or bigger?
It is quite small at the moment, so it's a little bit hard to see.
Okay.
You can use Control+, I think.
Yes. Is this okay?
Perfect.
Okay. So we just started up, or I had already opened a notebook running Python. So I will import VC DICOM. And then I will open a set of DICOM files. So I have this here in my directory. It's 5 files. It will complain a little bit because these were converted and not super good converted. Next, what we can do is that we want to see how is this looking in an overview. We want to have a small thumbnail of it. So we read the thumbnail. And some of you might recognize that this is a test image from OpenSlide. And this all looks good. We can go on and read out small regions out of this. So in this, I specify the position I want to read in pixels, the level I want to read on from the pyramid level, and the size that I want to read. And this is around here, I think. So we get this region out, and we can go on further looking in more detail. I will zoom in more and more into this corner, looking at level 2 instead, and also on the base layer. And what we are getting out now is pillow images, but you can also, if you want, to get the raw coded tiles with a different method. We can also look into what pixel spacing we have in each level. So here I read out the pixel spacing, also the MPP. The difference in how we define this is that pixel spacing is in millimeter per pixel and MPP is by micrometer per pixel. So it's just scaling. So see here that level 2 in this VSI has a pixel spacing of MPP of around 8 micrometer per pixel. And we can use this to read the same region as I did above, but instead read it by defining a millimeter area. So here I just multiply the above pixel position and pixel size by the pixel spacing to get the same region as above. And another thing that we've implemented is that you can read or you can scale your data to a specific MPP if you want. For example, you might want all your images to be of the same scale. We just define that we want to read out at 10 micrometers per pixel, and we then get a scaled image, this image, but scaled down to another solution. Going on, we will also now look at how we can use the VC DICOMizer to read other formats than DICOM. Indeed, I will change to this notebook. So the VC DICOMizer is pretty much based on VC DICOM, but it has this extra functionality that it can open other formats. So we'll import that one. And we will open now an SVS file from the OpenSlide test data set. And once we have done that, we can treat it just as we did with the DICOM file. So we can read a thumbnail. And this is the same image, so it should look exactly the same. We can then do the read region and so on and so on. And once we have opened it with and it's with VC DICOMizer, we can also save it as a. And when we do save, it will now save this imported VCI into DICOM formats instead. I'm just going to define a map here in my folder where it's going to be saved. And we can see now that it creates new files. This is the base layer file, and the rest of the files will create quickly once it has done the base layer. And here we get now the created files. I will close this.
Now you were muted, Eric. We lost you.
Sorry, someone else is talking in my room, so maybe someone muted because of that. I will go back to here. So I close the slide just in case I don't want to have it to leave it open. And I use VC DICOM to open this converted data set. And now I can again open it, but now I'm reading from the DICOM files that I have created here. And I will close this too. So,
And Eric?
Yeah.
Just a confirmation or question. So was it now that the whole conversion of that SVS into DICOM was like 5 seconds, or was that just a part of the image which was converted?
It was the whole. Let me check now how big this is, because this was not the biggest file. So the SVS file was only 180 megabytes. So that's part of why it's quick, but we will also come just in a minute to why it can be quick.
Okay, thanks.
So supported formats for the VC DICOMizer. We have some formats that we support with lossless conversion, meaning that we don't have to decompress and recompress when we convert. And these are then wrongly spelled Asperio, SVS, Hamamatsu NDPI, and Philips TIFF, and probably other TIFF formats. And this we then use the OpenTile tool, which is based on TIFF file, to losslessly just copy tiles from the, for example, SVS into the DICOM. So that's why SVS are very quick, because we don't have to do anything with the tile data other than copying it into a new file. Other formats are a little bit more tricky, and for those we have to actually do decoding and recompression. And those formats are Mirx, MRX, Hamamatsu, MMS, Wrestle, TIFF, Tana, BIF, and Size, CSI. And for some of these formats, we use OpenSlide to read them, and for Size, it is this tool, CSI file. And then there are other formats that we have not implemented or not tested. And the reason that we can make these files losslessly is that because they are non-overlapping, and these other formats, they have overlapping tiles or are very complicated. So that's why we leave it to OpenSlide, which is quite good at handling those formats. And next thing I will show is how we can add a little bit more metadata to these DICOM files. So we'll add the device and optical specimen, patient, and study module to this DICOM file that we create. Then we have this notebook. Now I'm importing a little bit of more functions. In the DICOMizer, we have some helper functions for creating this kind of modules that we want to make. So this is just the path that we are going to read from and where we're going to put it. First thing I'm going to create is this device module, which gives us information of or puts in metadata regarding the scanner that made this VSI. And there's this function called create device module, which we can specify manufacturer, model name, serial number, and so on. And we create a DICOM dataset that we can use and insert into our files. Next, we have a function creating a quite simple bright field optical path module. So this is specifying what kind of illumination was used to make the scan and what magnification. A little bit more complex is this specimen module, where we can define metadata regarding the staining of the slide and how it was prepared, how it was extracted from the patient, and so on. And to do that, we have to create the samples that are on the slide, so we can have multiple samples if you want. And we have this function called create sample, where we specify ID for a sample, what kind of stainings, the fixative, and bedding medium. And here you also say that, okay, this sample, it is coming from a specimen that we call specimen 0. And this specimen is a tissue specimen. It was extracted using dissection from the patient, and it comes from the liver. So we create this sample, and we insert that into the specimen module. So the specimen module, basically, it represents the slide and what you have on the slide. So we begin by specifying the slide ID to slide 0, and then we give it a list of samples, or in this case, just a single sample. And then we also have a patient module where we can say we can give name or ID or sex or age to the patient that the DICOM file is, or the image is on. And lastly, we have a study module where we can say when was this study done and give different IDs to it. But we leave that empty because I don't have any good information put there. And then I'm going to use the DICOMizer to convert this input SVS file and put it into this folder converted with metadata. And I'm going to insert all this module that we have created. And this should not take much longer than the previous conversion because it's the same file. And now I'm going to read this created file, or one of them, just to show how it looks like. So we have the same structure as I showed before in the presentation, where we see, okay, this is a JPEG baseline coded file. It is a VSI file, and now it is a pyramid file, and it's not resampled, so this is the base layer. You can see some of the metadata that we put in, for example, the manufacturer of the scanner and the model name. We can go down and see also the patient sex and age at extraction and patient ID. We can see more technical information, for example, that the file contains 23,000 frames and how big they are. They're 256 by 256 pixels. Down here we see starting off this specimen module that defines the slide and what is on the slide. So we can see that the slide is named slide 0. We can see that it is a slide and it is a cover slip that's made of glass. We can see that the specimens that are on the slide comes from liver and how that was made with staining, what kind of staining it was used, and so on. This is quite a long metadata block coming down here. Then are some more. Sorry,
Eric, we have some question in relation to this. So Max has 2 questions.
Yes.
He had the first we can take is that can coded values be used with some reference ontology, or is it just DICOM vocabularies?
Yes, that is a little bit depending. If we go up here, all these, for example, the stainings, they are defined in DICOM, so you can only use the ones, or you should only use the ones that are defined in specific tables in DICOM. But technically, you could use any code and coding scheme. When you come, so that applies to the stainings, fixative embedding medium, and sampling method, for example, or specimen types. These are all actual codes that are, or when we say that we have paraffin backs here, for example, this function will look up the code for paraffin backs that is defined in DICOM. But you could technically also use whatever code you want. When you come to anatomical site, you are free to use any code. So yeah.
Yeah, and the other question was, is there a NumPy array conversion functionality implemented?
So you can read out the tiles into NumPy, for example.
Yeah, so what is coming out from read region?
Yes, so what is coming out from read region is currently a pillow image, and that one you can very easy. Let me just do that. We can have an imported NumPy. Yes. What did I do wrong? Seek. Oh, I closed the file. Yeah. So just using NP as array on the image that you get from read region or another of those functions, we give you the NumPy array of it. Okay. So I was down here. Here we have the optical path module saying that the slide was created using bright field illumination and what kind of magnification was used. And at the end of the image or file, we have the pixel data where the actual tiles are stored. The next thing I want to demo is how we can convert more files. We are running out of time. Sorry. Is it okay if I continue? Faster?
Yeah, we have some time left.
We will create files based or create a data set, and we will create additional files based on this schema that we're creating for metadata. And that is this file here. So now I'm also going to import a schema that we have created that represents this, but in Python binding, so we can make XML files representing these entities. Quite simple. We define some codes, And here, let me show that there is a file. No, we are using the data set created by University of Marburg, and we read that with the pandas. So this is a sheet containing metadata regarding the image, slides, specimens, and biological being. And for each, I should also run this. How would I not? For each of these images that you find in this image metadata sheet, we find what slide is it related to, and from that we can create one of these slide entities, which we then code into XML here, making an XML slide object. And we do the same for example, for the observations that we find for this image, and for the samples that we find related to this slide, and for the specimens that we find, and for the biological beings. So for each image, we find what the slide is this image on, and we make an object for that in XML. And then for that slide, we take the sample, and for the sample, we take the specimen. For the specimen, we take the biological being. And for each of these entities, we make this kind of XML samples and XML observations, and we put them all in a big list. And in the end, we write these to XML files. So we're going to run this here, and we're going to convert, I think it's 5 or 6 files, and they will end up in here. I think maybe I forgot to empty this directory before I did this. That shouldn't matter. So, so I have the DICOM files here. This is double now. But more importantly, we have this XML files defining, for example, this image XML defines all the images that we have converted, saying that, okay, this image has the name image2, and it's made on slide 2. And it contains these DICOM files, and so on for image 3, that is on slide 3, and so on. And for the samples, we can see all the samples that we have created. So we have created one sample called slide 2, which is a slide. And this slide is made out of sample 2, and it has these staining attributes. And we can go and look at sample 2, which is just saying that this sample 2 is made out of specimen 4. Specimen 4 is a biological being, number 3. And it has been preserved using neutral buffer formalin, and it's from the pancreas of biological being number 3. And then we can see biological being number 3, it is a female, and that's all we now know about that biological being. And then we go on to the next slide. So it's the same thing. So this file now represents all the samples that we have in this data set. And observations are just containing diagnoses for each slide. So this references to the slide and say that this slide has the diagnosis that is normal tissue or is it invasive cancer, and so on. And what is next for this is that we will make more tools that will automate, for example, retrieving images and extracting metadata, and then convert it to DICOM using these type of tools, and prepare submissions files like I just showed, and also anonymize, validate, and submit this. And we hope that you will be used for this delivery report on find and first collected datasets by month 18. If you have any questions, you can email me or take them now. And if you have any questions or suggestions on the tools, you can create issues on the GitHub page. This is just links to all the tools and so on that not important to show here. Okay.
Thank you, Eric. We have some remaining questions from the chat, and
yeah,
maybe we can take them from top to bottom. And the first one is, I assume Z-stack scans can be saved in DICOM format. If this is true, is the reader able to read in all Z-stack layers?
Yes. You can save stacks either in separate files in DICOM or in separate files, and we see DICOM can read these set stacks and also read multiple optical paths.
Yes. And the second question was, is this available on GitHub? And I put the link in the chat.
Yep.
So it's available, and you can also just pip install it, I think.
Yes.
And then Joel Pettersson from Östergötland, he asked, we, Region Östergötland, converted some of our NDPI files to DICOM with a popular tool for DICOM conversion. And the DICOMizer provided by that is described here was order of magnitude faster. What makes this DICOMizer so much faster compared to the other software?
Yeah, it is that we do it losslessly, so we don't have to decode and recode. And also, if we are doing decoding or recoding, we use a quite fast JPEG coder. So that is the reason.
That was the questions from the chat. And if you have any more questions now, just turn on your mic and ask them if you want to.
Så tänker jag att man ändå vill visa ut skriva ut som en möjlighet att skriva ut lokalt.
Hello, here's Peter.
Hey.
Hi, Eric. So are there also plans to include these formats which are more proprietary, for example, together with Philips or together with the others?
Yes. But if such request, I mean, if you request, just please make an issue on the GitHub, and we will start looking into it. Because if we don't know that there is need for it, we are less likely to make it. But Philips iSyntax, for example, is one format that we are going to prioritize.
Good, thanks.
Okay.
Doesn't seem to be any more questions. And I guess if you have them, just email Eric and he will do his best. Could you put on the last two slides for me, Eric? So this has been a webinar that we provide in the Bigpicture Consortium. I think the attempt is to do one every month at least. So if you have any ideas of webinars that you want to hold, just email pmo@bigpicture.eu. And the next webinar that is coming up now is Eric, next slide.
Oh.
The next webinar is called End-to-End Learning for whole slide image classification. And you got an email, or at least I got an email earlier today with an invite link. And it's held by, let's see, I have it here. Yeah, it's held by a PhD student at Radboud under Geert. Stefan Duper. I probably butchered the name, but it sounds super interesting. So I'm probably going to be there, and hopefully you'll be there too. Is there something more we need to add? Paul?
No, nothing from my side. Thanks for the very interesting presentation. And
okay, thank you, everyone. Thank you everyone for being here and for your attention.
Thank you very much.
Thank you. Goodbye.
Thank you. Bye-bye.
Bye.
Thank you. Goodbye.